Hello, welcome to the second lecture of CS 527 Computer Systems. This lecture is also about clearing the basics of C programming. The actual content from the textbook will start from next class. Okay, so what I'll do, I'll run some basic code today. Let me create a folder here. Test. Okay, so this is a very simple program. So if we run this program, then we know the output, but still let me run it here. Okay, always on top. Let me run this code. GCC my program, then minus o out out dot o suppose out dot o. Okay, so now if I want, so this is the object file, executable file. Sorry, executable file is created out dot o. So if I run out dot o, my program is running here. Program is executing hello world. Okay, uh there is a spelling mistake. Okay, there is a spelling mistake, I'm ignoring. Okay, uh so now actually when we do this, when we perform this GCC, what internally there are different steps going on. First thing is pre-processing. After pre-processing, it is going for compiling, and then after compiling, it is going to assembly, and then after assembly, it is going to linking, and then final execution. So all these things are internally happening, but we don't know. So this we'll discuss today, that what internally is happening when you just give a this GCC command. And also let me use some macro here. Define max. Okay, so this is a simple program. So what do you think, what will be the output? Output is a greater than max or not. A is not greater than max, so it should print welcome to CSE. Let me run this code again. Okay, it is printing welcome to CSE. There should be a new line, and otherwise it will show like this. So if I use a new line here, then it will be appropriate, right? So maybe you will think that I'm spending time on basics, but that's my way. I always start from basic. Okay, so this is the program. So now what I'll do, I'll explain this program step by step. Okay, how? Let me go here and I'll remove this out. So there is nothing is there, only this program file is there. So as I said, the first thing is called pre-processing. Pre-processing. So what pre-processing done? How pre-processing we can do? Let me go for it. CPP, then my program, then I can say my program dot I. Okay, so this is the pre-processing thing. So let me open this for you. So see, this is after pre-processing. This is the file. There are some extra data in this file now. So these are actually the content of stdio.h, which are included here after pre-processing. And see, the max is removed. If you see here, we have compared a max, but here if you see in this pre-process file, it is 50. So this pre-processing, the macro is removed. So what pre-processing do? When we first step is pre-processing. So pre-processing will include the content of this header file in this program first of all, and then it will remove all this macro. So what it is doing, see, there are a lot of lines that actually up to here, most of the lines are from stdio.h. After stdio.h, it will remove the macros, and see, it is replacing all these macros. So this is the first step. This is called pre-processing. Compilation is not start yet. Same when normally we see GCC is the compiler, but GCC is the package. It's not just compiler. First it will go for pre-processing. After pre-processing, it will go for compiler. compiling. So what is the actual job of compiling? Compiler only compiles your code, that is a pre-processed code, to a assembly language, right? It is just assembly language. But what we have seen at the beginning, that if you go for GCC and then you compile the code, it is directly giving you a executable file, which we saved as out.o. That is an executable file, that is not just assembly file, right? So there are many other steps. So the steps actually pre-processing, then compiling, then compile will give you a assembly language code. Assembly language code, you already know, you have spent almost 2 months on assembly language code on RISC-V, so you know what is called assembly language code, right? Then there should be another assembler. That assembler will convert your assembly language code to a object file or a machine equivalent, machine language equivalent code. Okay, and then there should be a linker which will link all these objects. There will be object file, assembly language to object file, that will be done by assembler, and then there will be a linker which will link multiple object files, and then finally after link, then you'll the executable file will be ready. So all these steps one by one we'll discuss. Okay, so this is assembler, sorry, this is pre-process file, and now we'll compile this one. So to compile it, you have to run gcc minus capital S, and then my program.I, then minus o, my program.s. What this is doing, this is by this command, what we are doing, we are converting this p-process file into assembly language file and store it in my program.s. If we don't give minus s, then as gcc is not just an assembler, it's a package, so it will directly give you the executable file. We don't want to do this, we want to go for step by step. So we'll do this. If we do this, then see, it has created another file called .s. Open this file. Now if you open the file, you will see this code. This is an assembly language code, but this is not exactly the assembly language code that you know from the first half of this course, because you have started RISC-V, but this code is actually an x86 code, but it's an assembly language code. So I think from this file it is enough for you to just understand that this is an assembly language code. That will be enough for you. So now that's not the end, right? After assembly language code, we have to use an assembler, so that this assembly language code should be converted into a object file. Okay, so what we will do now, we'll again go here and we'll go for an assembler. So assembler is as my program.s minus o, then my program.o. See, now this is an object file. This is an object file. If you open it, it will be difficult to read. So let me open it from here. If I open it from here, my program.o, then you will see it like this. Why? Because it's an object file, so everything is not clear. That's fine, this is not our job. Maybe tomorrow I'll show you, because if you read the book in chapter 7, it has given the details about this object file, means what are the content of this object file. The complete structure is given in the book, but that we'll discuss tomorrow. And there is a command also in Ubuntu through which you can read the content of object file, but that is not important for today's lecture, so I'm ignoring all these things. Okay, so now you have the object file. So now you, since you have the object file, so what we have done yet, first we have done pre-process. After pre-processing, we got the minus I file, sorry, .I file. There is a pre-process file, then the pre-process file we compiled it, and after compiling, what we got, we got the assembly language file, that which was the .s file. Then from .s file we applied a assembler, and after applying assembler we got an object file. Now we have to apply the linking part. This is called last called linking. What linking will do, linking will combine multiple object files together. Okay, so here there is only one object file, but sometimes it's very required, sometimes it's required that we have to link multiple object file. I'll show you an example after this example where linking will be mandatory. Okay, so now what I will do, gcc and then my program.o minus o out.o. Now this file will link, and it will, after linking, it will create the executable file. So out.o is ready. So now if I go for out.o, it will print welcome to CSE. So you can, I think you are now you are getting the idea that how much step internally is required if you when you just go for GCC, right? So what I'll do again, I'll just remove this out.h again, remove sorry, out.o is gone. GCC, sorry, my program.c minus o out.o. That is the normal command that we keep to compile a code, right? This is the normal command. The moment we give this normal command, we get this out.o and we can run this out.o, right? So these are the two commands that we normally use to compile, and we say that okay, we compilation done, then we need to run. Okay, but that is not just compiling. GCC is a package, so internally all these things are happening, but these things are hidden. We are not getting the idea about what is internally happening. But all these things here, step by step, I have explained all these things to you. Now I'll show you a website, a web page. So since I'm using the web page, I'm giving them full credit. You can see the web page from where I'm explaining this diagram. I'm using that diagram to explain you, but you can also visit this web page or to understand the concept that I'm discussing in more detail. So for now, you just concentrate on this diagram. So what this diagram is saying, if you have a source file like this .c file, then first what it is doing the GCC or any compiler. First of all, it will go for a pre-processing part. Actually, it is not a compilation part. It is just pre-processing part. And after this, you will got a .i file that I have just explained you. And how to go for it, you can go for CPP command. CPP, it's a preprocessor command, CPP, and you can just revisit my video and you will understand what command I have used. And then you will go get .i file. Then that .i file will be given as an input to the compiler, and the compiler always gives the assembly language code. Compiler never gives object file or a machine language file. It will always give assembly language code. So that assembly language code to do this, what command we have used? We have used GCC. And if you want to save temporary the assembly language code temporarily, then you have to use -s command. Otherwise, it will directly, first of all, it will compile to assembly, and then directly it will store the object file. So if you want to see the assembly language code, you have to go for -S command. Then if you go for this, then assembly code will be generated here, and that you have to store, you can store in a file. We have stored it as .s file. And then there will be assembler you have to use. That we use the assembler called as, and then I have given input that .s file there, and that assembler is giving us a object file .o file. And then finally there will be a linker here which will link this object file with other libraries. If any other library we are using, for example, we are using here stdio.h, we are using, right? So if we are using stdio.h, then this linker will link all the functions, all the function definition with the, because in stdio.h only the function declarations are there. So for all the functions definition maybe in some other library object, so that object will be linked here. So the two terms that I'm using, definition and declaration, that I will explain you with our own header files. And then finally it is creating the object file. That object file we have stored as out.o, and then that object file you can execute. Okay, to execute this object file, how to execute it? There is a program is there in operating system which is called loader. So how to start a program? To understand this, you should also understand how a program works. So if you remember your first half of this course, then you must have understand that initially to execute any program, there is a register in processor called program counter, right? And every time after executing instruction, program counter increments, and then that meaning of that is that which is the next instruction to be executed, right? But initially if you assume that, if suppose this is the executable file, so first thing when you want to execute is that the point from where the execution should start, execution of this program should start, that address should be loaded in the program counter, right? So that part will be done by the loader. So these two terms are very important, linker and loader, with compiler. Okay, so you can visit, I can read more detail about all these things that I'm discussing from this page. So in this particular example, what I'll show you, that there are two files here. Let me open these two files first. This is file one. I will close all the uh, previous files here. So this is my file one, and this is my file two. Just quickly look the content of file one first. So please read this function program once. This is a very simple program. what I am doing here. Yeah, there are two variables a and b, and then I'm calling a function calculate. Suppose it's a so it's a calculate a and b. So that function, so assume that that function is adding these two variables and returning the value. So what value it will print here? The result is percent %d r, sorry, percent %d new line r. So what value it will print? It should print 40, right? Or let me say 30. So it should print 50. But what normally we do after this, we should write the function here, right? So here, now this is a complete function. If you can run this file, and it will give you output. So here, this is called function definition. This is called definition. This is called declaration, and this is function calling. So declaration, definition, and calling all are required. So sometimes we also call it function prototype, right? So but if this call is, if I remove it from here and I put it here, uh, here, then this declaration is not very important for this particular case, because we are defining the function before calling it, because we are calling it here and we are defining it before. So that's fine in that case. But normally it's a common programming practice that always use declaration, even if you if it is not important that where you are defining the function, I mean before calling it or after calling it, always is use the declaration. But these are CS101 concepts, so I'm not explaining this in detail. What I am doing here is, the function definition is not in this file. Function definition is in this file. See, calculate is function is written here, and remaining things are written here. So that is perfectly fine, you can write this type of code. But only thing here is, if you want to use the function here which is not defined in this file, then you have to declare it here. No means it may be possible that the function is declared here also, but in any file, if you want to use or call a function which is not defined in that file, then you have to declare that file. Okay, so you have declared it. So how we will compile the code here? So this is the case. Then let me clear everything first. Now gcc file1.c file2.c minus o out.o. See, it is now out.o is ready. So I can run out.o, result is 50, right? So how to compile this code? If there are multiple files, this is the command. This is the command gcc. You have to write all the file names, file1.c, file2.c minus o out. Okay, this is the technique. But what is happening internally? Do you think how this gcc is performing all this task internally? That we will discuss. So instead of using the gcc complete package, what we will do now, we will go step by step. First of all, what we will do, we will go for cpp file1.c. we will write it file1.i. What it is created, this c file is now converted to preprocessor. Just understand that I am not doing anything with file2.c. I'm just working on file1.c. So file1.c is now converted to preprocess file, and now I will compile it. Gcc minus capital S file1.i, and I'll store it as file1.s. Right now, this file is now stored in assembly code. Now what next? What is the next step? Next step is assembler, which will create an object file. So assembler will take file1.s minus o. Now file1.o. Now object file of file1.o, that is object file of this, object of this file is created. So first object is created. In the same way, we also need to create the object of this file too. So first object file is created. So now you can see the two object files are created. Okay, this out.o is the old thing. Let me remove it. Let me remove it. This is old. This is the from my previous, this is old. So now this is the scenario. First of all, the file 1.c has created I, then O, then S, then O. Same for file.2, we have created I, then S, then O. Now these are the two important files, file 1.o and file 2.o. Now for both the files, we have performed pre-processing, compiling, and assembling. All these three things is done. Now what we will do, we'll go for linking. As I have said, what link purpose of linking is linking multiple object files. So here these two object files need to be linked. So what we'll do, gcc file 1.o, then file 2.o, then minus o out.o. See, now the linking is done and final executable is stored in out.o. So now if I go for out.o, it is executing the program and result is now stored. Result is 50, it is storing. So that is the expected result. So now I hope you understand the basic purpose of all these steps: pre-processing, compiling, assembling, and linking. The purpose of linking is very important. So here, don't just think that it is linking these two object files. It's also required. It is also linking some other library objects maybe. Okay. So now what I have said in my previous case, I said that in linking also resolve the connection between function definition and a function declaration and a function definition. What I was trying to mean is, you can see, if you go for file1.c, we are calling that function, but function is not defined in this particular file. It is not defined, it just declare it. And now you remember, now you just revise what I have done. I have compiled this file separately. So when I was compiling this file, first it is converted to .i, file.i, then file1.i, then file1 uh, dot assembly language. It means what? That when I'm compiling this particular file, I am not looking this particular file. It is not necessary. Without looking that file, compiler is converting this to assembly language, and for that purpose the declaration is very important, because if I have declared this function, it means that when I'll compile this file, when I'm calling this function, it will say that okay, compile, this is a function, it is not, it is just declared here, so it will be defined in some other file, just compile the whatever is here. So here you can see, we can get file1.o, that means object file of file1.c, this file, without any connection with file2.c. That means there is no function definition, only function declaration is there. And then a separately the object file of this will be created. Now there are two object file, file1.o and file2.o. And if you just or try to run file1.o, it will not run, because there is no function definition of cal. Only function declaration is there. Definition must be there. That's why linking is necessary. So linking will link these two objects so that the function definition should be available, and then only your program will run. That's why the final executable has a combination of everything. So the same thing is happening with stdio.h also. So if you remember my previous example, when what I did, that after converting to I have opened the .i file, and I've shown you the content of this .i file. That was a huge content. Why it was used? Because the complete content of stdio.h was copied there, but the content of stdio.h is mostly the function declarations. So the functions, those are written in stdio.h, maybe in some other file or in other objects. Okay, so during the linking phase, that linking is also necessary. That's why in the diagram of that web page, it was the purpose of linker was showing that it is linking your object file with library object files. Okay, and then only you are getting the final executable. So the concept of compilation part is done. So I'm quickly explaining you another concept, which is called why when we need header file, right? I hope you understand it, but still it is better sometime. Suppose this file is here, no problem, but suppose here there is another file, uh, integer multiplication, sorry, integer add, and integer x, integer y. And now what I am doing here is, it returns x plus y, and here it is what it is doing is return add a comma b. Are you getting my point? What I am trying to do here? What I this function is same. I'm not doing anything here. It's just calling cal function, and here this cal function is calling another function which is add. Now, do you think this file will this program will compile? How will compile it? Uh, I'll remove all this file. Let me remove all this file. These are not required now. All these internal steps I have already explained you, but now I'll not go to these details. Now the steps how to run a code. This is the program, right? This is the command, right? This is the file. Sorry, it should be .c now because I am not going for internal steps. I want to directly compile. So if I try to compile it, I don't think it will compile. I think it will give error. It is giving some error, right? Why it is giving error or warning? Why? Because if you go here and if you check here what we are doing here in this particular file, there is nothing wrong in file 1.c, but in file 2.c we are calling a function called add before declaring it, before defining it. So we have defined the function here, but before defining we are trying to call that function. So that will be, that will not that will give a error. So the best way is to declare this function here. Now there will not be any issue. So compile, see, perfectly fine. It's compiled and this executable is also created. You can run this executable. So result is 50 as expected, right? So that's why I said that it's better to use function definition in every file if you are calling that function. There is no harm. You can also use integer cal here. There is no harm. You can use that also. Means a function can be declared in multiple files, but a function can be defined only once. There is no harm. If you compile this code now also, it will be compiled without any warnings or errors, right? Fine. So that's why a better way to do this is, instead of including all the header files here and then again file 1.c, what we normally do is we remove that all these things from here, and what we normally do is how to open a new file. Okay, fine. What we do actually, okay, save. Okay, so what I have done here, I have created a separate header file called myheader.h, and now what I will do here, I will include that header file here, hash include my in my header.h, and this, since this is my header file, so I'll use this, and the same header file I'll also include in file 1. Yeah, and I'll remove all this declaration, right? Now it's easy, right? What we have to do, just create a separate header file and declare all the functions there, or write all the function prototype in this header file, and now just include that header file here. And now also if you come give the same command, it will execute. See, it is executing. You no need to explicitly mention the header file .h, but still it will run. So that's why the header files are important. So this point is not actually related to the previous point. The concept of the linking internal part of GCC I have already explained. This is a separate part that I'm explaining, that why header file is important. Very easy, the concept of BTech level thing, but I'm explaining it. Okay, so this is how we have to use header files. Now I'll go for another important topic, that is, suppose instead of these two files that I am using here in this program, folder to 2, assume that there are many files, there are hundred thousands of files in your in this project, and every time when you just try to compile your code, it takes a lot of time. Yes, it's possible. For example, the simulator that I work in my computer architecture, if you just give a compile command, normally it takes at least 10 to 15 minutes to compile. If you need to compile everything, suppose there is a here there are thousands of files, but after letting thousands of files, it you have compiled it once and it was perfectly running. And now after some time, you just need to change something in a particular file. Okay, and then after this, if you just give another GCC command that way I have given in terminal, then again it will take same amount of time to execute. But that should not be the case, right? That should be something that we should only compile that particular file, and then we have to create a separate object file, and then we can link that object file with other object files. That should be the ideal case, right? But that is difficult to handle. But what we can do here, I can follow the previous steps again. So for this, what I have done here, you can just see I have repeat the same step that I have used previously. What I have done here, I have separately created object file for file 1.0. I have separately created object file for file 2.0, and then I have just combined these two and created out.o, and it is giving the expected output as it is. So all this part I have already explained you previously. So now what I will do here, just assume that I need to change something in file 2.c. So let me open file 2.c. Okay, this is the file 2.c, and I want to change something. What I want to change, let me assume that instead of x plus 1, it should be x star y. Uh, it should be x star y, right? So now if I want to compile, what I want to do, I have, since I have only changed file 2.c and I have not changed anything in file 1.c, what I'm expecting is that I will only do repeat the steps of file 2.c. Okay, and create the object file 2.o separately, and I'll not do anything for file 1.o photo. So what I'll do, I'll start from here, cpp file, this should be file 2.o is created. Now what I have done, I have only created file 2.0. And now the next is I'll just combine these two with this command. I think uh, what is the command? This is the command, right? GCC file 1.0 and file 2.0. Let me just increase. This is the command. So again, out.o is created. So these steps should be followed. So every time what you need to do is, if you have just compiled a particular file, for example file.c, and there are many files are there. So instead of changing all this file, what we can do here, if there are separate object files are there, then we just need to change the object file of means recreate the object file of that file only, and then we have to link them again. GCC, this line is the linker, then I have to link this new file 2.0 with the other old object files, and then you have to create the new executive. So how normally we compile a code, this is the code that we will write first, and then and I say that this is the command to execute. Actually, this is the command to execute, and I said if you compile, if you type this command here and if you press here, it will just create you out.o final executable. So if there is only final executable, then it means that every time if you change any of this file 1 or file 2, and if you apply this command, then this command will, every time it will compile the entire project. It will not go for just one file, it will go for entire project. So how, this is not the correct step. Correct step I explained here, that one by one you have to create object files separately, and then you have to go for linking. Okay, that's why the purpose of linking is also clear. But how to do this, this is a long this is a lengthy step now, so no one do this. So here, to save time, we are increasing the we are making it more complex, but there is a way to make it simple, right? And that is called the concept of makefile, right? So I cannot explain you the complete under means concept of makefile, but that is very important for you. You spend some time on makefile, go to internet and study it. It is not available in your textbook, but when I'll give you assignment, I will force you to use makefile. Let me create a makefile here. What I will do here, all, then here file. Actually, GCC minus C is actually, it will directly give you the object file of file one. You can also instead of going for .I .s, and then you can also check this GCC minus C file one, then it will just compile and give you the object file of file one. Okay, the same thing I'll do for file two also. So what is happening in makefile, you can write multiple targets. These are targets: target one, target two, target three. And normally when you try to execute makefile, it's normally start from the first target if you have not explicitly defined from which target it should start executing. Okay, and so every target has some dependencies. So in this target, this target is dependent on these two files, file 1.0 and file 2.0, not 0, sorry, file 2.0. Okay, so in this target, there is a command. What command this target will execute? This target will execute GCC file 1.0, file 2.0 minus O out. You understand what is this? It is actually the linking part of these two objects. So, and this target is saying that it is depend on these two. So, before making these two file ready, this will not execute. So, this dependent file will first execute, because these the compilation of this is depend on this. So first of all, it will go to this target file 1.0, and file 1.0 is dependent on file 1.c. So if file 1.0 is not there, then you cannot execute this target. And the command here is gcc minus c. So file 1.c will create file 1.0. This target will create file 1.0 from by this command. And then this is also this target also need file 2.0. So this is the target file 2.0. Dependent file is file 2.c. And then if file 2.c is there, then it will perform this command, and it is creating file 2.0. So from file 2.0, this target, you can write this target name different also, no need to write the same name like file 2.0. But this target is creating file 2.0, this target is creating file 1.0. And now when I'll come here again in this target, these files are ready, so I can link it. So what I'm actually doing here is I'm compiling file 1 separately, creating file 1.0 as I was doing previously, and I'm compiling file 2 separately, I'm storing it in file 2.0, and now I'm linking it here. So now the beauty of makefile is how now, let me go here again. This is our folder, uh, clean. Okay, so now what I need to do here is just write make. If I go for make, then see what it has done. Just make, it is compile everything, and your out.o is ready. And now you can run this code. Result is 600. Expected result 600, right? Because what we have done, we have changed file 2.c, and instead of add, we are now multiplying it, if you remember. So now 600 is perfectly fine answer. Now if you change anything in file.c, and if you again go for make command, then it will only compile the required files and not the everything. So in that case, it will only create file.o as a new object, and then it will link that new object with the other existing objects. That's the main advantage of makefile. Okay, so I'm stopping today's lecture here. And what I'm expecting from your side is that you will study the concept of makefile by this weekend. I have already given you some task in lecture one, and I'm giving you another task that you should understand the concept of makefile, and also you will practice how you can go for the pre-processing file, then assembler file, and also whatever I have explained today, you also practice it and be prepared for the actual content of this course by next week. Thank you for watching this video.